Okay, so let's finish up assumption number 2 that Niels Bohr had when he went in to solve this problem about the spectrum. Okay? The hydrogen spectrum and these weird numbers. Well, we're going to take what this here tells us. This is our second assumption, sort of summarized. Circumference of the orbit has to equal an integer number of de Broglie wavelengths. And remember, de Broglie wavelengths, h over mv, for an object of mass m moving at speed v, right? Also, we know the circumference is 2 pi r, right? You learned that before you met me, hopefully. So, we can put these together and write it this way. So 2 pi r circumference equals n h over m sub e v. M sub e, this little m sub e simply means mass of electron, because that's what we're talking about. Okay. And this can be rearranged to be written me vr equals n times h with a bar across. Look at that. H with a bar across it. What does that mean? Do not worry. H with a bar across it is simply a short way of writing h over 2 pi. Okay. In fact, in physics, whenever you see any quantity with a bar through it like that, it means that quantity divided by 2 pi. It just happens that h over 2 pi shows up all over the place, and it's actually a very important quantity in quantum physics. So I think physicists got tired of writing every time and just put a slash to the h, and h bar was born. Okay, so h bar shows up everywhere, but it's just Planck's constant divided by 2 pi is all that it is. This is how we write assumption number 2. That's assumption number 2 right there. Okay? And what I want you to notice is this. N equals 1, 2, 3, dot, dot, dot. N cannot take on any value. It can't be 4.7. It can't be negative 12. Okay? It can't be 17.1. It can't be pi. N is only equals certain these integer numbers. Actually, not even integers, counting numbers. 1, 2, 3, 4. Which means that if n can only have certain values, look at this, then MVR can only have certain values. Not all values are available. This is the first place where we see that atoms, electrons within atoms, only exist in certain states, discrete states. Right now, those states are denoted by the number, the letter N. 1, 2, 3, whatever. We have state number 1, we have state number 2, we have state number 3. So how do I have it worded here? This is our first example of what's known as a quantum number. Okay. We'll see other quantum numbers, but this is actually what this is precisely what you call in chemistry the principal quantum number, N. Okay, you've seen it before. This is where it first came up. All right, it was in Bohr's model of the atom. That's where N comes from. It's the same N. So that's assumption number 3. So what I want you to see is that the electron can exist in different states. These are different quantum states. We're going to drop the word quantum. These are just states. And what these different values of N tell us is that the electron or the atom can only exist in certain discrete states. Okay? We'll say more about what that means later, but just keep that phrase in mind. The last thing I want to do is talk about the third assumption. Bohr's third and final assumption. Okay. Is that the n equals 1, 2, 3, dot, 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 states each have their own value of, wow, that sound, energy. So the electron, or the atom, when it's in state 1, n equals 1, has a different energy than when it's in state 2. And a different energy again when it's in state 3, and 4, and 5, and 6, and 7, and 8. And that dot, dot, dot means there's really no limit. There's an infinite number of states the electron can be in a hydrogen atom. Okay? Each has their own energy. And how do I have it worded here? Pick a different color. His assumption went on to say, the third assumption said that light is emitted when the electron goes from any one state. It can change states. If you put an electron in the n equals, if you put a hydrogen atom in the n equals 3 state, it will not stay there. It will jump to a lower state. So light is emitted when the electron goes from any one state to any lower state. And this light has energy HF, right? That's the energy of light. Planck's constant times the frequency equals the initial energy minus the final. It's not final minus initial. This is not a delta E in that formal sense. But the light has this much energy. That is assumption 3. So if a given hydrogen atom is in state number 5 and falls down to state number 2, which we'll see later on, it tends to do, okay, it will emit light. And that light will not have any old random energy. It will have a very distinct energy, and that energy is given by the difference in the energy of the initial state and the final state. Okay, we'll see this in much more detail in a few lectures from now. But I want you to see this assumption is going into the theory. Okay?